Alright, let's continue. So, last time we ended with a question. Why was this okay? We had sine of x, cosine of x, dx. And we saw that that could end up in like 3 different yet equally correct ways. Do you remember what those were? Was it sine squared x over 4? That sine squared x over 2. Okay, differentiate that using the chain rule. The 2's would cancel. You multiply by the derivative inside, and it would work. We also have minus cosine squared x over 2. And the last one was something with a cosine.
Sine 2x.
Sine 2x. It was just sine 2x, like what was the answer?
That's just how you started off.
Oh, yeah, no, the final answer, just give me the, it was cosine 2x something, right? What was it?
Let's do it again.
Jeez. Aren't you guys paying attention? Like it's, you apply the trig identity, so that's 1/2 sine 2x integral dx. Integrate that, that becomes 1/4 minus cosine 2x. Let's see. Okay, so that's that. Right. So you did it, you got this. Your friend did it, you got that. Look in the textbook, it shows that. Why is this okay? Yeah?
Is it because they can all, like the plus c, they can all differ by a constant?
Right,
Equal.
that's the important thing. We are allowed to differ it by a constant. Remember what the indefinite integral of f of x dx meant, right? We said that this was equal to big F of x plus c, where big F is any antiderivative of the small f. So any function that when you differentiate it, you get the small f and you add a c would be an answer. And a corollary of that, what that would necessarily mean, is that if you get 2 functions that look different in the formula part, what that must mean is that they must be different from each other by a constant factor. So it means that each of these you'd be able to write as a constant times the other one. Do we even see how that would even work? Because we actually have, by the way, another trig identity that I do expect you guys to remember is cosine of 2x. You guys remember what that is? Do you know how that looks in at least 3 ways? So applying the addition formula, that is cosine squared x minus sine squared x. Right? So you can already see that this one is just actually a sum of those 2. So he's different from these 2 by a constant automatically. You could also write this as 2 cosine squared x minus 1. Right? So that guy is off of that by a constant by a minus 1 factor. We'll multiply by a minus 1/4. It's also 1 minus 2 sine squared x. So all these guys, they actually play well to each other. You can connect all of them by a constant. So while they look different in terms of a formula, they're all just one constant off from each other. And that makes it okay. As long as when you differentiate, you get the original, sine x times cosine x, you're fine. Each of them, consequently, if we're given more information in terms of what some initial value is, the plus c's in all of these might look different, but they'll work out so that the outputs of all the functions would be the same. it. That's why that was okay. So moving on to the last situation for the sine and cosine. So let's look at sine nx cosine nx dx, where both are even. Now, when both of them are even, what you do here is you again use another trig identity. So to remember all our trig identities, use the half lemma formulas or double lemma formulas. They're the same thing really. So what you do is change the trig functions. You change both of them if they both appear by you know that the cosine squared of x is actually 1/2 times 1 plus cosine 2x. And your sine squared of x is actually 1/2 times 1 minus cosine 2x. And that actually comes from this, right? Cosine 2x equals that. Using this, the second equation, this equals that, I can solve for cosine, I would get this. Using this equation, setting this equals to that, I can solve for sine squared, and I would get that. And so you would plug these in, and you go from a situation where you can have a square to a trig function that's not squared. Those guys are easier to deal with. And depending on the situation, you might have to do this multiple times, but let's look at an example. Say we want to do sine sine squared x. Should stop there. So if you want to integrate sine squared, another common mistake students often make is that they see one trig function to a power and they just think they can integrate it based on how the bases behave. Yes, we know how to integrate sine of x. We would get negative cosine of x. However, sine squared is very different from sine of x. The answer is not negative cosine squared. You can't actually do that. So that is in fact a mistake that's listed in the syllabus of thinking that the integral of a product is the product of the integrals. That is what would give you cosine squared x, and that's actually incorrect. You see a sine squared by itself or a cosine squared by itself, you're going to use these formulas to change it. Into that. Then, bless you. Now you can integrate easily. The integral of 1 is just going to be x. The integral of cosine 2x. Of course, technically you do a substitution if u equals 2x, but we're beyond that at this point. You know you're just going to end up dividing by a half. Right? Whenever your du is going to be a constant, you can just divide by that constant. It doesn't work if it's not a constant. And that would be the answer. That's how you'd integrate this, right? Which is not the same as cosine squared. You have both of them showing up. Right? And cosine squared very similar here, except you have a plus sign in the middle. Plus sign in the middle here. So you have a plus sign here. So if you have that, they're both even. So you can't like save a factor of 1. You're not going to really get away with that. But what you can do is you can change both at the same time. So I'm going to change this to 1/2 of 1 minus cosine 2x. I'm going to change this to 1/2 of 1 plus cosine 2x. Both the 1/2s come out, give me a quarter. And at this point, what we would do is expand and simplify. So we can multiply this out. That's going to be 1. Well, that's 1 minus cosine squared 2x, right? That's the difference of squares here. Now you see there's a square on the double angle, we don't know how to deal with squares, not directly anyway. So what we do is we can apply this rule yet again, but apply it to this trig function. So it's going to be 1/4 times 1 minus 1/2 times 1 plus cosine 4x, you double the angle. So this is going to be 1/4 times 1 minus 1/2, it's 1/2. You could factor out 1/2 if you wanted to. And we can integrate each of those. Integrate 1/2, you get 1/2 times x. Integrate this, you're just going to divide by the 4, so that's 1/8 sine 4x. That's your integral there. Other options? Here's another way to do this. Which you can notice that you could have applied it here also, by the way. So you had sine squared x, cosine squared x dx. You can think of this as sine x cosine x all squared. But I know that my sine x cosine x, that's actually 1/2 sine 2x. So this just actually becomes 1/4 sine squared 2x. And if you look at that, you'll notice that that's actually what you had here. 1 minus cosine squared is actually sine squared. Could have applied that here. So many ways you can actually spin this cat. And at this point, with the sine squared, we're going to apply that formula. So it's 1/2, which gives me 1/8, times 1 minus cosine 4x. And so this gives me 1/8 x minus 1/4 sine 4x.
It's the integral of that, right?
The integral of this. Dx plus c, which you'll notice it's the same as that. So moral of the story, be very comfortable with your trig identities. You'll need to be able to apply them in to kind of weasel your way out of various situations. Which again falls in line with the larger strategy that we saw last time. Of just knowing, basically, anytime you want to actually apply some strategy, really what you're doing is in the back of your head, there's some rule or formula that you know about, and you're just trying to finagle things to look like that rule or formula. Right? That's often what we were doing last time. And the trick, one thing that I wanted you guys to get out of last time is that you don't actually do any change unless you can see that there's some formula that you're trying to change it to. Right? So you would know in the back of your mind, yes, the integral of x to the n. Right, so you have all these formulas in your head, x to the n plus 1 over n plus 1 plus c, when your n is not minus 1. You know that 1 over x is ln of absolute value of x. You know that the integral of e to the kx is 1 over k e to the kx. Let's see, k not equals 0. We know that the integral of ln of x, now we actually know that that's x ln x minus x. We know the integral of like secant squared x. We know that that's tangent etc. Right? So you have all these rules in your head, or you should, right? All those formulas, right? Like the things that I tend to ask you in problem 1 on a quiz. Complete the rule, state the formula. All that stuff is in your head. Once you're looking at a typical problem, your first goal, how can I move this thing around, jiggle it around so that it looks like one of these rules that I have in my head, right? Like a sine x dx, which I know gives me a minus cosine of x, or plus c. Or a cosine of x, which I know looks like a positive sine of x plus c, right? So if I'm given this thing, the first thing I'm going to try to do is try to finagle it to look like, notice at the end, I end up looking like a 1 where this rule applies, and then I end up looking like a cosine of 4x where this rule applies, right? My goal is to change it to look like some rule that I know. So of course, step 1 is to know all the rules, like you know them by heart. You're very intimately acquainted with the rules, right? All your trig identities, all your integration rules, all your differentiation rules, you know them very well like the back of your hand. Then, whenever you're faced with a problem, your goal is, how do I get that to look like one of these? Right? And 1, you can either try to do a substitution to make it look like that. So right away, for example, your cosine to the 4x doesn't look like your rule. But if you let u equals 4x, your du equals 4 dx, then you can factor out that 1/4 cosine u du. I can get it to look like that rule. Once I get it to look like that rule, now I know I just apply the rule. That's a sine. But now I replace my u, so that's 1/4 sine of 4x plus c, right? Which is where this guy came from. So sometimes we're doing things, nothing is random. I never make a random step. And yes, last class I was going to ask you guys for input, and you guys were guessing all sorts of random things. And I didn't just do that just to laugh at you guys flailing around uselessly, right? It's actually to get you guys to know what is a good guess, what is a bad guess, what does it feel like when I'm guessing and going down the right path, as opposed to just digging myself deeper in the hole, right? You need to get used to what is a good line of thought to go down. And the first goal is to, what gets me closer to looking like one of these guys? That's always it. If I do this thing I'm thinking of doing, does it look closer to this? No? Forget it, it's the wrong path. If I do this, does it look closer? Yeah. Is that the answer? I don't know, but it's closer to the answer. So you just go down that path, right? Every guess you make, everything you try to move around, is to the purpose of getting to look like one of these rules that you know, and then you apply it. And in Calc 2, as I mentioned, it's not as straightforward to get to the rules as in Calc 1. In Calc 1, it's pretty much sitting there, it automatically looks like a rule. Like, oh, that's just the chain rule, that's just the product rule. In Calc 2, sometimes you kind of have to finesse things a little bit, right? But ultimately, you do something to get it to look like a simpler version that you know how to deal with. That's kind of the idea, right? Still bonus problem. How do you do this one? So it doesn't quite fit any of the previous situations that I mentioned, like the power of cosine to some integer and the power of sine to some integer. But you might be able to do something similar. What are you guys thinking? Yeah?
Never mind.
What did you see? Just go. Yeah.
Could we save a factor of cosine and then change cosine 2x to 1 plus cosine of 2x?
Change cosine.
Change cosine squared x to 1 plus cosine 2x. You could do that, right? Or no?
You could, but should you? Right now, what you just did is you're creating a situation where you have some trig functions having the angle 2x and some having x.
Okay.
Now you're creating a situation where you have, the angles are different between the various trig functions. That's kind of, yeah.
U equals sine x.
Right, my d is going to be cosine x. What happens to this guy? Yeah?
Could you change cosine squared x to 1 minus sine squared x?
Okay, then? Now we can,
Like
you
I
can go.
was saying another way.
What was the other way?
Like
Well, what you said before now
like
works.
U equals sine x.
Yeah. At this point, u equals sine x makes a lot of
And
sense.
then du equals cosine x dx.
Right? So you get
and-
that part,
and,
and now this is just another u.
And
right?
then it becomes cosine square x divided by root u.
So this would be 1 minus u squared, because u is sine of x, over the radical of u. And cosine of x dx, well, that's just your du. Now, that's going to be 1 over radical u, which is u to the minus 1/2, minus u squared divided by u to the 1/2, that's 4/2 minus 1/2. That's u to the 3/2. And hey, that looks like the power rule. Right, so at this point you're like, oh, I know a rule for that. It's a power rule right here. So now, you can apply the rule, you add 1 to the power. So that's u to the 1/2 divided by the new power. Add 1 to the power, 5/2 divided by the new power. So that's actually 2 times the square root of sine of x minus 2/5 times the square root of sine of x to the 5th. So, didn't quite fit the jargon, but you saw, there's an odd power of cosine. I mean, the other situation it kind of works out. So maybe if I save a factor or something might work out, turns out it did. So, was a guess, but it's not like a total shot in the dark. There's some strategy that you know works in some situation. Hey, it might work in this situation. Ultimately, it will get me to a point via substitution where I can look like one of my basic rules. So that's how you can deal with that. Another thing, I mentioned this before, but let's do it again. So probably you guys have done substitution and it's always u equals, but you should be aware that this is an idea we're going to actually use later today. I don't know, maybe we'll get to it. But your substitution doesn't always have to be the variable u. Sometimes you can actually make your substitution work for you in further simplifying the situation. So for example, if I know I want to substitute something where something is under a radical, I might just substitute a square instead, right? If it was under a cube root, I might substitute a cube instead. So you could have done like a u squared equals sine x. Differentiate both sides. And so now what happens is, this would be 1 minus, your sine squared would of course be u to the 4th. Your radical of sine would of course be u, because your sine is u squared, the radical cancels. And your cosine x dx is now 2u du. You notice now, u's cancel. That looks even nicer, no fractional powers, right? You can still get to the same thing, that's u minus u to the 5th over 5. and times 2.
Yeah.
And at this point, you plug in your u. Your u from here, you'll notice, is the square root of sine x. And so this is 2 times the square root of sine x minus 2 times the square root of sine x to the 5th over 5 plus c. Get to the same answer, but with slightly less mental or psychological turmoil. So you can actually get your substitution to work for you even more than just simplifying your function. You can simplify it even further. Completely optional, but it's a thing that you should probably start thinking about. It'll help you in more complicated situations. So you can do a u squared substitution, a u cubed substitution, and a completely different kind of substitution, like a trig substitution, which hopefully we'll get to. But yeah. But the main idea, try to make the thing that I'm looking at look like a basic rule that I have. And we have various methods of getting this done. So substitution is the main one. We now know integration by parts, and we now again know about, we can use trig identities to help us do that. But overall, that's kind of the main goal. Let's look at other types. Secants and tangents. And as I said, I won't ask you about cosecants and cotangents because they function, no pun intended, very similarly to the secant and tangent. If you know how to deal with secants and tangents, you'll automatically know how to deal with cosecants and cotangents. So we're only going to focus on secants and tangents. It's useful here to know how do you actually integrate a tangent? How do you actually integrate a secant? Let's find those first. Okay, go. What do you do?
Change it to the sine of the cosine.
U equals sine.
U equals sine.
Cosine x.
No, u equals cosine x, right? Because your du is going to be the sine of x, negative sine of x dx, and you have that sine of x dx right here. Right? You said u equals sine, your du would be cosine, but you don't have cosine, you actually have 1 over cosine. So your du would equal to negative sine x, and what you would then do this, it just gives you, well, the negative integral of 1 over u du. Hey, that looks like a basic rule. That's ln of u plus c. So this is actually minus ln of cosine of x plus c. So that's a new formula that we know now. We know that by heart. A lot of places won't actually write it that way though, because you know the negative sign on the outside is not very aesthetic. So one thing you can do is remember how logarithms work. You can take a constant multiple and you can actually move it up as a power. That's a law of logarithms. And so now we have cosine to the negative 1 power, that's just secant. So that's now, this is now something we know. The integral of tangent of x is ln of secant of x. The absolute value of secant of x. It's also equal to the negative ln of cosine. It's up to you which one you want to remember, but I kind of remember the top one first because it doesn't have a negative sign. Okay. What about the secant of x? Anyone knows how you do that one? Yeah?
Could you rewrite the secant to the cosine?
And?
You could change it to cosine. Wait. cosine x to the -1. Actually, never mind.
Yeah, can't really do anything. Yeah. Admittedly, this one is kind of a weird one. So I'm going to show you how this is traditionally computed. It's not going to be very satisfactory, but it's another kind of a trick you can have in your arsenal. And later on, I'll actually show you another way to compute this. But here's how it's traditionally done. You multiply and divide by something strange out of nowhere. Like you multiply by secant x plus tangent x over secant x plus tangent x. Now don't ask me what possessed the first person to do this, to actually do this. I have no idea. But once you see it, it's ingenious. What is going to happen here? You're going to have a secant squared plus a secant tangent. Now do you see what to do?
U equals tan x.
And then your du would be secant squared. Yeah, well, in that case, this will be a problem,
Yeah.
and that will be a problem. Yeah?
Change secant square x to 1 over cosine square x. And then plus 1 plus sine over cosine square. Like,
1 over cosine squared.
yeah.
And
Plus,
I leave everyone else the same?
no, secant x tangent x equals 1 plus sine x over cosine square x.
And the denominator would be 1 over cosine plus,
Okay, there's another one, like 1 plus sine x. Oh, never mind. Yeah.
so you're trying to prove trig identities, changing everyone to sines and cosines, definitely a nice thing to do. Does it help here?
No.
Like, I don't know what to do with that. Like, what are we going to do at this point?
And then the denominator will be 1 plus sine x over cosine x, and then you flip it, like, because that's divide.
Okay. And then?
Like the top part will be 1 plus sine x over.
So this will end up being cosine x. 1 plus sine x will be on the bottom. And then we would have
you can cross them out, like 1 plus sine x. That's
over cosine squared x.
yeah.
okay. And so this would all become,
Sorry about my English, but
1 over
that's
cosine squared.
yeah.
And what's that?
So it's 1 over cosine.
So that's where we started.
Yeah, I think we're, yeah, it's definitely, no. Valiant effort, but no.
Okay.
Changing to sines and cosines, often that does take you somewhere. Here, no, you'll kind of just flail around. No. We don't need any more trig identities at this point,
Okay.
if that helps. There's something we can do here. Yeah.
If we split it into two different integrals and then use
good substitution.
What would you substitute? So like a secant squared divided by a secant plus tangent, and then a secant tangent divided by a secant plus tangent?
Yeah, I guess so.
You have an idea?
Maybe split the fraction, so it's like secant squared x over secant x plus tangent x plus secant x tan x over tan x.
Okay, and how would you do the first one?
Secant squared x over
If you look at this fraction, how would you do with that?
would you use another trig identity?
As in, do what? You don't need any more trig identities here. And while splitting up a fraction, that is also often a very good thing to do. It's not going to help you here. It's like really right in front of you. It's like you don't need to actually move anything else.
Could you substitute secant x plus tan x? Make that du?
Want to substitute the denominator?
Mm-hmm.
Okay. What is the derivative of secant x?
Secant x tan x.
What's the derivative of tangent x?
Secant squared x.
Oh my god, look at that! This guy here is actually that guy over there. Like multiplying by that weird thing actually gets this to work out. So we have, that's just 1 over u du. Looks like a basic rule, that's ln of u. So you pretty much get ln of secant x plus tangent x plus c. And that's a rule we know now. Integral of secant is ln of secant x plus tangent x. That is now a part of our basic rules. And it's a very clever substitution that you kind of multiply and divide by some weird thing to get it to work out. But it turns out by doing that substitution, your secant x, the numerator just becomes the derivative of the denominator. Cosecant it's a very similar thing. You'd multiply by cosecant minus cotangent or something. And the numerator would actually work out to be the derivative of the denominator. So yeah, that's how you do with tangent. The integral of tangent is ln of absolute value of secant plus c. The integral of secant is ln of absolute value of secant plus tangent plus c. Okay, so now that we have the basics down, let's go back to so here are the cases that we're going to look at. So there's case 1. Case 1 occurs when m is even and if tan is present. Usually you want this to be at least 4. Case 2 is when n is odd and secant is present. And so you already start to see these guys are kind of weird. Now, case 3, pretty much anything else, all other cases. Now, in case 1, the idea here is to save a secant squared, change all other secants. Using, you actually know that 1 plus tangent squared is secant squared. In this case, let me I'll actually write that out a little nicer, clearer. But that's basically what you do in this case. You'll save a secant squared, change all other secants to tangents using that identity. Then you do a u equals tangent substitution. If n is odd, you would save a factor of tangent times secant, change all other tangents to secants using that same identity, and do a u equals secant substitution. In all other cases, you try something and hope it works out. That's the best I can do. Like it already starts getting too complicated here. There's no like general formula for the other cases. That's Calc 2 for you. That's how it works. So in case 1. Say you have secant to the 4th x tangent cubed x. Now it doesn't actually matter whether the power of tangent is odd or even. The fact that the power of secant is even and at least 4 allows you to use this rule. So what you would do is you break that apart, save a factor of the secant squared, detach that and leave it at the end. You're going to change all other secants to tangents using this. Notice that I can write secant as 1 plus tangent squared. And now, if I do u equals tangent, my du is going to give me that secant squared that I had saved over here. And the integral is going to just become, I'm just going to replace all those tangents with u's. So that's u cubed plus u to the 5th, and that's u to the 4th over 4 plus u to the 6 over 6 plus c. Tangent to the 4th x over 4 plus tangent to the 6th x over 6 plus c.
So it's always gonna end up with a tangent in the answer? It's never gonna have a secant?
In this situation, yes. With this method, in this situation, yeah, because you're gonna save a secant squared, everyone else you're gonna transform to tangents. Now once everyone else is a tangent, you're doing a u equals tangent, and your integral is therefore going to just have tangents in it. If we look at case 2, basically you're going to save a factor of secant x tan x. This one actually happens to be a problem that you can actually use either case 1 or case 2 to look at, because case 2 has the tangent being odd and a secant actually showing up. But I'll manipulate this a little bit more. Change all tangent x to the secant x using that identity. 1 plus tangent squared equals secant squared. Do a u equals secant x substitution. Or t equals secant, whatever you want to do. And then you are going to just integrate. Example, let's say I have the integral of secant to the 5th x tangent to the cubed x. So secant is present, the power of tangent is odd. What I'm going to do is I'm going to pop off one of those secants and one of those tangents. I'm going to put it at the end, secant x tangent x. Now, this leaves me with secant to the fourth left over here and a tangent to the squared left over here. Now what I'm going to do is I'm going to change all the tangents to secants. Now a tangent squared is going to be a secant squared minus 1. And at this point I can do a u equals secant. Your du is going to be the secant x tangent x. And that allows me to change this integral into something nice, like the power. Secant, so secant to the 7th x over 7 minus secant to the 5th of x. That's the integral of that. How would you do that one? We're actually out of time. Let me give you some to work on then. We'll pick up with on Friday. The other examples we would have done be A, B. Try to do a tangent cubed, C. Try to do a secant x tangent squared. And a D. Try to do a secant cubed. Okay, so we'll stop there. We'll do these next time and then start trig substitution. But of course, try to finish them before then. I'll see you guys on Friday.
Thank you.
Okay.